Welcome to a quick review of refraction. So we're going to get into the math of it real quick. We're not going to go through every question in the notes here, but let's get through some of this business. This question here is a nice leading question. What wave characteristic depends on the medium? If you remember, the medium determines wave. What's the next word? What's the next word? Word is speed. So, of course, if you change the medium, you change the wave speed. And this is a big one. This comes up a lot. All right. So let's talk about changing medium. That's what this is really bringing us to. So we're going to change our medium. Here it is. And changing medium basically is refraction. What happens when a wave goes from one medium into a new medium? In fact, let me back up to our summary page. You may want to have this nice summary page on point. Back to page 19. It says here refracted. Refracted, a definition is the wave passes from one medium into a new medium. And some things change, some things don't. But the things that change are as follows. The speed changes, the wavelength changes, and usually you get a bending. Now you watch some videos on this, usually you get a change in direction. There's one situation where the direction does not change, and you saw that in the second straw video with the oil in the water, when you look straight down from above. So basically when you look down on a surface that's perpendicular to you, right along that perpendicular line, you won't notice that bending. All right, so let's jump back over to this refraction. So we're going to a new medium. So what changes, what doesn't change? That's the point of this little section right here. So here we go. First thing, what does not change? Frequency and period. Now, you may say, all right, well, that seems arbitrary. How am I going to remember that? Well, if you remember, the frequency of light is its color. So it's not really a great test, but light equals color, so light frequency. A simple way to try to remember this is basically put something in the water. Does it change color? You're in a new medium now. Did the straw look a different color when it was in the oil or the water or the air? And the answer was no. The color stayed the same. So a nice way to help you remember that, color is frequency, so frequency stays the same. Sound frequency, actually a little eye will pop up there in the corner, or go to the top of the video. I'll put a link to my singing a note underwater and then out of the water. Now there's bubbling in the water, but when it comes in the water, out of the water, you still hear the same do. It's the same note. Sound frequency is the note or the pitch. Leave it as pitch, why not? So that stays the same. Do they have underwater speakers for music? Yes. If you've ever been in a pool with an underwater speaker, the music sounds just fine. Those are the notes. So the frequency of sound, the color of light, they don't change when you change medium. So the frequency and period, they stay the same. Important to keep track of what does not change. All right, next, speed changes. Now we have an equation. Equation is V, speed, equals frequency times wavelength. Well, looking at this equation, it kind of tells you what's going to happen next. If we know that frequency stays the same when you switch media, well, speed changes, wavelength must, in order to maintain this equality, the wavelength has to also change. In fact, the wavelength, if you notice here, will change the same way that the speed changes. They have a direct relationship when you change medium. So V goes up, wavelength goes up, and the reverse, of course. Finally, the angle of the wave ray usually changes or appears to bend. The only exception there was when it was at 90 degrees, and 90 degrees to the surface, which is also known as 0 degrees from the normal. Let's type that in over there. That's an important one. The angle of the wave ray usually changes, and this is if the ray is not that tiny, along the normal line, which means, no, my code won't work, angle equals 0 degrees. That's when it does not. That's the exception. Let's put the word exception in there. Exception. So usually. All right, put that all together, you get refraction. So we're going to jump right to it. All right, we're going to go right over here. So how do we quantify refraction on a sketch? Here's the way you'll normally see this. I have a few pre-drawn lines that are going to help us get through this. Basically, here's what happens. You have an incident ray. Here it is. This is your incident ray. Your incident ray is just the light ray coming in. Now this light ray, in the absence of any new medium, will just continue on its way. In fact, this light ray, let's line this up just right. If it's in air right now, it's in medium 1 air. If there were no block of lucite, this light ray would, let me line it up just right, would continue off this way in a nice straight path. However, we're encountering lucite. And so at that point of interaction, at that point where you meet the boundary between the media, something new happens. That's something's called refraction. If you remember, frequency and period stay the same, speed changes, wavelength changes, angle usually changes. So how do we keep track of drawing this diagram? You can't draw the speed, you can't draw the wavelength, you can calculate them, but the only thing you can draw is the angle. And so that's generally what these diagrams are for. So how do we do it? Well, you need a normal line. Here is the boundary. The normal line, which we learned in reflection, is perpendicular to the boundary. Normal means perpendicular in math. So you need to take your normal line like we did with reflection and put it here. This is perpendicular. Good. Except we need it right at the point of intersection. Boom. There it go. Okay. Now, next, let me stretch this down here a little bit. Stretch this normal line out. Don't be shy with your normal line. It should go through the boundary and it should be plenty long. You can sketch this out on a piece of paper and do the drawing yourself. Okay, so we need the angle of incidence. So right now, we're not going to measure the angle of incidence this way because the protractor is not on it. You could measure it this way. There we go. Line up your little crosshair. Angle of incidence. Count in groups of 10 like we've discussed. That's the simplest way. Will not make a mistake. So 10, 20, 30, 40, 50. Looks like it's about 50 degrees. It might be slightly off. Let's keep it simple for this. Let's call it 50.0 degrees. It's hard to write, so I'm probably going to abandon sig fig soon. 50 degrees. By the way, you could also hold the protractor this way, and it would correctly give you 50 degrees as well. Remember, you were measuring away from the normal line. This is the normal line, 10, 20, 30, 40, 50. That one actually says 50. Okay, good. So we've got an angle of incidence, 50 degrees. Now, what happens every time a wave meets a boundary? Tar! Where is it? Here it is. Every time a wave hits a boundary, here's the note. When a wave reaches boundary, a combination of transmission, absorption, and reflection occur. So absorption, it just becomes lower amplitude. Reflection bounces off at that same angle. We practiced that. Transmission is it goes into the new medium. Now we are actually just quantifying transmission. That's all refraction really is. Refraction is a special case of transmission when you have a new medium, a new different medium. So notice we also have reflection. Let's jump back over here, back over to page 24, and let's see what we do. Well, the easiest thing to draw, some of this light is going to reflect, so draw the reflection. You're good at this. You've practiced this already. Run that over here. And so if angle of incidence was 50, the reflected ray will also be 50. So where is 50? Well, 50 is 50 away from the normal. 10, 20, 30, 40, 50. It's actually at the 40 on the protractor, but that's 50 degrees. Sometimes I like this setup because it allows you to do the incident and the reflected at the same time. Of course, you would take this and turn this and make it into a straight edge and line it all up. But where I lose out on writing, I gain with drawing lines. So this should start at that point of impact and run through the 50-degree dot. There is our reflected ray. Reflected ray. All right, reflected ray. A little intense with that font. There you go. Here's our reflected ray. Good. All right, now, that's not the only thing that happens. We said tar. Every time you hit the boundary. Now come over here, I'll write it. Tar. Tar. So this thing comes over here, hits the boundary. Some of it transmits, some of it absorbs, some of it reflects. We just drew the reflection. Good. Lighten this up a little bit. The absorption, again, you're not going to draw it here. You could draw it with thickness of arrow, but that's not something we generally do. What about the transmitted part? Well, we said here, if this incident ray didn't hit anything, there were no medium 2, there were no lucite. You say lucite, what's lucite? Don't worry about that too much. What you'll see here in the reference table is on page 2, we have the absolute indices of refraction. So there's a bunch of materials here, a bunch of translucent materials. Light can travel through them, ranging from air all the way through, actually I'll say diamond. Now why air through diamond? Air has the lowest number, diamond has the highest number on this list. These numbers are actually measures of how much light refracts, which basically means how much the speed changes, how much the wavelength changes, how much the angle changes. Not how much the frequency changes. In fact, the frequency is always the same. And for this chart, we assume a frequency of 5.09 times 10 to the 14th hertz, which is somewhere in the yellow range up here. That is perhaps the most common, or roughly the most common or ubiquitous light on Earth, because that is roughly the highest intensity light that the sun spits out. That's why it looks yellow. Okay, so these materials we'll refer to. Let's jump back over here. So here's lucite. It's just a clear plastic. All right. Now, this incident ray does not actually follow this dashed line that we drew here through the lucite. In fact, when it hits a lucite, kind of like the fish tank, it bends. I got a nice block like this in class I would have shown you. The question is, how much does it bend? Well, there's a nice, easy formula for that. By the way, just backtrack one step. We can mark our angle of reflection as 50.0 degrees. All right, so bigger issue. How do we figure out the angle? So we know the incident ray is going to be somewhere over here. In fact, just as a piece of advice for figuring these out, whenever a ray comes and hits a boundary, you can imagine this like your 4 quadrants in math class. It's nice for you to recognize, okay, well, the incident ray here is in quadrant 3, the reflected ray is in quadrant 2, and the transmitted ray is going to be in quadrant 1 in this case. Of course, if the incident ray were somewhere else, if the incident ray started in quadrant 4, the transmitted would be in quadrant 2. So you have to pay attention to that. One of the reasons this is good is so that you never get confused that the light ray bounces off of the normal line. We draw the normal line dashed because it is make-believe. There is no actual boundary here, vertical boundary here. There's nothing for it to bounce off. There is no light ray going into what looks like our quadrant 2 right here. So stay away from that. All right, we have an idea. It should be somewhere in quadrant 1. Where does it go? Well, we got Snell's Law. Here's what Snell's Law looks like. You actually use this on W80. I had you do this. N1 sine theta 1 equals N2 sine theta 2. So perhaps the ugliest of the wave equations in our reference table, but notice, N means absolute index of refraction. That's from that chart we just looked at. So there's an N1 and an N2. Well, that makes sense. We're changing medium. So there should be 2 different media, meaning 2 different indices of refraction, hence N1, N2. Now, we're also going to have 2 different angles. That's your theta 1, that's your theta 2. So run your numbers. That's it. How do we do this? Let's scroll down here and do this one. So N, there we go, 1 sine, I'll just put a O for theta, 1 equals N2 sine theta 2. Well, plug it in. Not a big deal. N1 is air. N2 is lucite. So if we go check the chart, check the chart, air is 1, lucite is 1.50. So this substituted becomes 1 for air, sine, air, the angle in air was 50 degrees. So 50 degrees equals, N2 is lucite, 1.50, sine theta 2. So we got to find theta 2. That's not too hard. Theta 2 is just going to be inverse sine of the quantity 1.00, which is just 1, it's not changing anything, sine 50 degrees the whole thing divided by 1.50. And so if you do this, let's run this real quick. You can do this in your calculator on your phone. Make sure you put in the degree first. You put in the 50, then you hit sign, then you hit divide 1.50. Make sure your degrees, by the way. Then you hit that second function sign, and you end up with about 31 degrees. Got about 30.7. Let's keep it simple. I'm not measuring that more carefully right now anyway. Comes out about 31 degrees. So boom, we're ready to go. Draw it. How do we do that? Well, it's nice that we roughly know where it's supposed to go, so we don't measure it in a strange area. Bring your protractor back. Where is about 31 degrees? Well, 31 degrees away from the normal. The normal is here, not away from the boundary. And so let's go 31 degrees away from the normal. There's 10, 20, 30, 31 is right there. Good. You'll have to turn your protractor, make it a straight edge. Line up these two locations and draw your arrow. I'm actually just going to pull an arrow from over here and set it up. So it's going to go from this spot. Now it does not, it's going to go in the direction of the 31 degrees. It does not go on forever. It stops right there. It stops right there and has another tar, of course. Hits a new boundary. So you're going to get a transmit and absorb and a reflect. Again, by the way, this one over here now is our, shrink it down a little. Now I was going to erase incident ray, but the truth is you shouldn't, because yes, it is our transmitted ray right here. Transmitted ray. However, when that ray strikes a new boundary, that transmitted ray has just become the new incident ray. That's all. All right. So then what happens? You do the whole thing again. Hits a new boundary. At that boundary, you need a new normal line. We practice this in reflection, but yes, I should actually show you how to do it again. Drawing the normal line, you need to go exactly to the point of intersection. You put a dot there. You put a dot at 90. You take your protractor, the little 1-2 step, rotate it, use it as a straight edge, and you will draw it. I'll just drag it over here. Put your new normal line in. There we go, the new normal. Good, something like that. Okay, so there's our new normal line, and what happens at this boundary? Tar, once again. And so how do you actually figure out? Well, not too hard. Angle of incidence equals angle of reflection. So there will be another reflection here, but you have to find the angle. Now, you should know the angle from geometry class. The boundaries of this medium happen to be parallel. So this is like a transversal, which means if we were 31 away over here, we're going to be 31 away over here, and yeah, it looks right, which means the reflection should be 31 away on the other side of the normal. So the reflected ray, 10, 20, 31, put a little dot there. You turn your protractor so that it's ready to draw the line. I'm going to get mine out of the way and just draw my little reflection in here. So here is my reflected ray through that, and boom, till it hits the boundary, and you get another tar. We're not going to keep going with this. Of course it would. You'll get some that comes out and some that reflects. Now we avoided the transmitted part of this. Now, if this ray were to continue without reaching a new medium, it would go off in this direction. However, that is not the correct direction because we are entering a new medium. So this can't be the answer. Where's it going to go? Some of you might actually have an instinct here on this one, and your instinct is probably correct. If we do Snell's Law, I call this n1 sine theta 1 equals n2 sine theta 2. If we do this for the top boundary, what we will find here N1 this time will be lucite, so we'll make this 1.50. The incoming angle is 31 degrees. N1 will be air, 1.00, sine theta 2. Theta 2 is going to now be 1.50 sine 31 degrees. Actually, if you remember, we rounded, it was 30.7. Divide by this, and of course, it's going to bring us exactly back to 50 degrees. So it actually brings you right back to the same angle it started. Now this works when the two boundaries are parallel. If they are not, don't expect it to work. All right. However, there's no magic to it. You can just do Snell's Law to figure it out. So where is our 51 degrees? Or 50, sorry. 10, 20, 30, 40, 50. Here's the dot. You rotate to draw. But I'm going to get mine out of the way. And boom. There we go. Whoop, there it is. So, and there's your ray diagram for an incident ray in air, 50 degrees to a lucite boundary. And so you get a reflection at 50, you get a transmitted at 31. The 31 transmitted is now incident at 31 on the top surface, reflects at 31, and refracts or transmits back out into the air, back out to 50. This one down here, by the way, would also reflect at 31, would bring a little arrow over this way, and it would transmit back out at 50 as well this way, and it would be parallel to this reflected ray. So if you saw this in class, if you're in a dark enough room, you get it multiple. You actually see, like you can run a laser, you see the reflected ray and the transmitted ray. You hold it up on the board and you see little shadows on the board, little markings on the board of the laser. So there it is. That's it. Now the other pieces I would show you on the other pages, I could just show you right here. The other questions you might get are, we talked about what changes. Well, for all of these problems we're doing, we're going to be using this set frequency, this yellow frequency. So the frequency and of course the period. By the way, if you're wondering, well, why is period the same? Well, period is just 1 over frequency. So if the frequency stays the same, then the period has to stay the same. So the period's going to be 1 over this number, which is about roughly 0.2 times 10 to the minus 14th, or 2 times 10 to the minus 15th seconds, something like that. It's a period roughly. It's a little less than that, actually. Small period. Okay, anyway, if you remember, by the way, 3-word definitions: frequency, cycles per time, period, time per cycle. That's a lot of cycles per time there. All right, anyway, let's come back over here. The things you could be asked about are the speed and the wavelength. So how would you get speed in air? Well, actually, we got a nice little equation for that there. Here it is, speed equation. So we have this one, speed equals frequency times wavelength, but we don't know lambda, so we're not going to use that one yet. This other one for speed, n equals c over v. So c is the speed of light in a vacuum. That's a set number that's right here in the front of your reference table, rounded to 3.00 times 10 to the 8th meters per second. The v is what we're trying to find. That's the speed. And n is the index of refraction, right here on PRT2. So doing this actually shouldn't be so bad. The equation they provided, sorry, I don't like doing fractions with the slash, but it is what it is. So we're going to do this for air right now. So n air equals c over v air. That's the way to do it. So n air, if we're trying to find v air, we can rearrange this. V air will equal c over n air. All right, well, v air will equal 3.00 times 10 to the 8th meters per second. Move us over a little bit. Divided by 1.00. And of course, it comes out to 3.00 times 10 to the 8th meters per second. So often when we talk about speed of light in a vacuum and speed of light in air, we use the same number. However, one of the extra credits I have for you, it's in the notes too, but I'll just tell it to you here. figure out the speed of light in air to 7 sig figs. So you got to look up the index of refraction for air to higher sig figs, and also the speed of light to higher sig figs, and you will see it's not exactly the same. If you had to do this for lucite, this is equally simple. There's a little more math to it, but instead of air, it will become now, let's put an L for lucite. And then, of course, the speed in lucite is C over the index for lucite. And if you go look up the index for lucite, it is 1.50. And so this brings it down to a crawl. So it's 2 times 10 to the 8th meters per second. All right. Finally, if you needed to get the wavelength for these, how would we do it? The wavelength for air. Move this down here a little bit. I'm not going to mess around with the symbols too much because they're bothersome. So I'm going to have our closest approximation to wavelength is we're just going to take a Y and just flip it around. Come on, Y. There you go. It's not really a wavelength. Let's see. Let us flip left, right. Okay. It looks a little bit like it. Why not? So wavelength equals, well, you have that equation. V equals lambda. So speed equals frequency times wavelength. And if you rearrange this, wavelength is going to equal, come on now, good, speed over frequency. So being that you found the speed, it's pretty easy now, V over F. And so here, we don't need to run it all. You found the speed. So for air, it's 3 times 10 to the 8th. For lucite, sorry, this should say L over here for lucite. For lucite, this is 2 times 10 to the 8th over the frequency, which we had up here, 5.09 times 10 to the 14th, and boom, you'll get your wavelength. Wavelength comes out pretty small, somewhere in the order like 589 nanometers. That's times 10 to the negative 9th meters. There is another equation that I want to show you, which is actually very useful. This one down here. Looks kind of ugly, so people tend to leave it alone. But this one is nice. Not only is it useful, it also is telling. So if you know the 2 indices and one of the speeds, you get the other speed. Or the 2 indices and one of the wavelengths, you can get the other wavelength, etc. It's got a bunch of ratios here. So that's one way to go about this over here. So if you knew the speed in air, we had that equation you just saw, like N2 is to N1 as, I don't want to write the wavelength symbol again. Bring it over here. So one way you can go about this is something like this. Once you find the wavelength in air, so instead of 2 and 1, why don't we make it air and lucite is to, and notice the indices actually switch. So it's not going to be air over lucite, it's going to be lucite over air. So lucite, there we go. Actually, make it bigger and subscript it. Over, so complicated, right? I hope you see where I'm going with this. Hope you feel my struggle on this. All right. This one's going to be air. And of course, we need to divide the 2. Not really worth writing again. It's very problematic to write. Okay. Point is, this other equation does exist, this multi-equation, and sometimes it's helpful. Sometimes you don't have to go through frequency. You can just use this. This is also helpful in that it's showing the indices reverse. If you have a higher index material, that's the 2, then actually that corresponds to a lower speed and a smaller wavelength. But we'll worry about that more in our next lesson. We're going to talk about some of the trends of refraction and just try to nail those down. So that's basically the long and the short of it. That's really it. That's your full lesson on this. And there's a couple little details here and there that you can flesh out. One thing I thought you might like to see here, I'm not going to do all the math too fancy, but this is a screenshot of the fish tank. And if you look closely, this is the path in the water, and this is the path through the chalk. So what I did is I sketched this out and I lined it up. So this line goes right through the laser light from the chalk. That's outside the tank, that's in the air. This line down here, turn up your brightness, turn off the lights in your room if you can't see it, that's a laser light in the water. So this is an actual example we're looking at here. You know, this is not just, there you go, it looks pretty lined up. Let's move over a little. This one too. Looks pretty lined up. This is actually what we saw happen. And so if you throw in a boundary line, where they hit is going to be the boundary. Yes, I pre-drew these. I came and checked it out. You throw a normal line in here. Get out of here. Come on, normal line. There you go. Throw a normal line in here. There it is. And you do a couple measurements. Oh, you find out some pretty cool stuff. Like, first off, what's the angle of incidence? Well, let's set this up right here. Angle of incidence looks like about, actually it's probably nice to write in white on this page. Looks like it's going about 10, 20, 30, 40, 50. Looks like maybe on mine 57.5 degrees is our angle of incidence. 57.5. Now this is going from air into water over here, into Piranha's fish tank. And so again, if you're on rush for time, you don't have to watch this, but I'm going to show you real quick how this is pretty cool how it works out. So N, let's do this all in white so you can see it. Good. Shrink it down a little. All right. 1 sine theta 1 equals N2 sine theta 2. And so if you do this real quick, let's make ourselves a little room. What angle should it be in the water? Well, N1 was air, 1.00, sine 57.5 degrees equals N2 is water. And if you go look it up over here, fish tank water is 1.33. So 0.33 sine theta 2. What should theta 2 come out to? Theta 2 is going to equal inverse sine of the quantity 1 sine 57.5 divided by 1.33. And what does that come out to? If you run it in your calculator, remember, if you have the small calculator, you're going to get a little crazy here. First do 57.5, then you sine it. Times 1 doesn't do anything. Divide 1.33, then you inverse sine it, and you get about 39 degrees. So this should come out to about theta 2 equals 39 degrees, roughly. And what's pretty cool is, again, I did not doctor this. I actually just took this and said, let me see what it comes out to. What's pretty cool is, line this up, and boom, check that out. Tell me that ain't a win. 10, 20, 30, just before the 50 there, that's 39 degrees. As predicted, actually it came out like 39.3 degrees, as predicted. So in fact, we saw this work. Pretty cool. All right, try to do those calculation problems, and then in the end, we'll next lesson rather, we'll get on some of the fancy stuff. Peace.